Hi guys, this is part 2 of video 7-2, still for Thursday, February 23rd. In this part, we're going to be finding particular solutions. So last time we found general solutions because there was the plus C, which could represent any number. Any number could go in for it, and we would have a solution, a particular solution. So find the particular solution to the given differential equation. So you're given this differential equation because it's an equation and there's a derivative involved. And so what we want to do is follow these steps. So please write these down and then we'll follow them. First, you find the general solution. That's with the plus C. Then you use what's called the initial condition. So this here is the equation. This is the initial condition because they're giving you a condition about this particular solution. So use the initial condition to find the correct C. And then rewrite the general solution with the C from step 2. All right, so you take the differential equation and you begin separating its variables. It's already in Leibniz notation, so I'm going to separate the variables. So I get dr equals negative pi sine of pi theta. And right away, I see a function within a function. I know that I'm going to have to take the antiderivative, so I'm probably going to need to use substitution. All right, so I should recognize that as soon as I have sine of something other than just plain theta. Okay, and then r's are all over here, thetas are all over there. So now we can do the antiderivative. This here we just get r equals. All right, now I'm going to need use substitution, all right? And guys, I was doing this earlier, and follow what I do carefully because this is very fast, even if you're writing in pen. So I'm going to let u equal pi theta. So du equals pi d theta. So d theta equals 1 over pi du. And I'm just going to do the substitutions right in here. I'm not going to bother writing it all over again. So right in here, what went in for that was u, okay? What goes in for d theta is 1 over pi du. Okay, so just like that. I see right away that those cancel, okay? And so this becomes, I'll bring the negative out front, but you don't have to, sine of u du, okay? So in the past, I would have rewritten a totally new integral with the substitution. Now I'm just like crossing things out. I'm trying to be more efficient about it. Okay, so now I know a lot of you are struggling with antiderivatives of sine and cosine because they're very similar, except one will have the opposite sign, S-I-G-N, of the original. So this might be helpful, guys. You could think it through if you just write this. So I'll write here, I'll write f, and then I'll write f prime. And so this chart might be helpful to memorize. So, and I'll go sine, cosine, negative cosine. And then I get the derivatives. So cosine, negative sine, so positive sine. If you just think it through like that once, write down these 3 options, find the derivatives, then you could easily go take a look at these and go backwards to the original. So this is, so I'll bring down the r equals, bring down that negative, and then in here I'll just have the antiderivative of sine. So there's positive sine, its antiderivative is negative cosine. You could have done it a little bit differently, and then plus c. And now I can put u back in, so we get that r is equal to positive cosine of pi theta plus c. Okay, that is called the general solution. Now, so that was number 1. Now number 2, find the initial condition, or use the initial condition to find c. Guys, when they're telling me this, the input is theta, all right, and the output is r. So they're telling me that when theta equals 0, r equals 0. So, all right, so this is my initial condition. So, oh, this is a mess, sorry. So I'm going to say, so I plug in 0 for r, 0 for theta. So I get 0 equals, I'll get cosine of 0, which is 1, plus c. So c equals -1. So I end up with r equals cosine of pi theta minus 1. That is the particular solution. It is the solution to this differential equation for which these conditions are true. Alrighty, one more, guys. So, given the differential equation right here, use separation of variables to find the general solution. Simplify your answer as much as possible. Find the particular solution of this equation given the initial condition y equals 3 when x equals 0. Okay, now... Okay, so I think I'm going to cross this out. I'm not going to... All right, let's cross out the simplify your answer as much as possible. I'm going to make another video on doing that. Okay, so first, for number 1, I convert to Leibniz notation. So dy over dx equals 8y. Then I try to separate the variables. So I get dy equals 8x dx. Yep, variables separated. Okay, antiderivative. So y is equal to 4x plus... This is a y. My bad. All right, so never mind that. That's a y. Okay, so I thought it was too easy. So 1 over y dy equals 8 dx. You could have had 1 over 8y, but try to make it easy on yourself because you're going to have to take the antiderivative eventually. And then we'll go like this. Okay, so this is the natural log of the absolute value of y equals 8x plus c. All right, this is the general solution. It's not really simplified. The directions that we crossed out would mean to solve for y. All right, you'll have to put a base of e on either side, and it gets a little bit complicated, so we'll talk about that some other time. But this is the general solution. All right, one form of it anyway. So that's number 1. And then for number 2, find the particular solution of this equation given this initial condition, y equals 3 when x equals 0. So I'm just going to take my general solution and I'm going to plug 3 in where there used to be a y and 0 in where there used to be an x. And I end up with the natural log of, you don't need the absolute values anymore because 3 is already positive, equals c. So the particular solution with this differential, or I'm sorry, with this initial condition is this 8x plus natural log of 3. Okay, so that is the particular solution to that differential equation. Okay, guys, so there was that, and I will see you soon. Bye-bye.